Okay, I want to take a look at an inverse square field. So remember, here's the general formula for an inverse square field, just some constant over the magnitude of my position vector cubed times my position vector. I'm working in 3 space now. I could use that formula for a vector in 2 space as well. My position vector would then just be xy. But here I want to actually take the divergence and the curl of an inverse square field. So for that I need to be in 3 space. Okay. So what I'm going to need to do is just write out what my inverse square field looks like in terms of the individual component functions so that I can then calculate the divergence and the curl. Okay. So I'm going to suggest that you pause the video, give yourself lots of space, either lots of scrap paper or a very large clean whiteboard, because there's a lot of tedious calculations. See if you can write out your vector field component-wise and calculate the divergence and curl. Then tune back in and check your work. Welcome back. Okay. So if I wanted to write f in terms of x, y, and z, I would say, okay, that's c over the magnitude of r is just the square root of x squared plus y squared plus z squared. We're cubing that. And then that's times x, y, z. So what I'm going to do is this scalar valued function here, I'm going to distribute to each of these components. And I think as I do that, I'm just going to rewrite this as x squared plus y squared plus z squared all to the negative 3/2. So I'm going to get cx times x squared plus y squared plus z squared to the negative 3/2. So the c here multiplied by the x, and then I just rewrote that as this quantity to the negative 3/2. And then I'll get cy times x squared plus y squared plus z squared to the negative 3/2. And then I'll get cz times x squared plus y squared plus z squared to the negative 3/2. Okay, so those are my component functions. I could name them p, q, and r if I don't want to have to copy them a gazillion times. If I'm calculating the divergence of f, that's just del dotted with f. So that's the del operator, whose components are just the partial derivative operators, dotted with p, q, r. So that's just going to be the partial of p with respect to x, plus the partial of q with respect to y, plus the partial of r with respect to z. Get a better marker here. Okay, so I'm going to calculate each one of these things. Because this kind of takes some space, I'm just going to do it one at a time. If I calculate the partial of p with respect to x, so I'm looking at this, I'm just going to use product rule. The partial of cx is just c, and then that gets multiplied by x squared plus y squared plus z squared to the negative 3/2. Plus cx gets multiplied by the derivative of this. So actually that's going to bring down a negative 3/2. So let me just put that in front. And then I still have that cx. So negative 3/2 cx x squared plus y squared plus z squared to the negative 5/2. And then chain rule times the partial with respect to x of that inside part, which will give me a 2x. Now, I can simplify a little bit here. I can cancel those 2's, and I might want to combine those x's. So that's giving me a cx squared. So let's see, that's c times x squared plus y squared plus z squared to the negative 3/2 minus 3cx squared times x squared plus y squared plus z squared to the negative 3/2. Excellent. So now I need to take the partial of q with respect to y. That's going to be incredibly similar because this function has the same basic form as this, except instead of having a cx here, we've got a cy, but I'm taking the partial of it with respect to y. So I'm basically doing the same work over again, just with different variables. Okay. So I'm going to get partial of cy is just c, and that's times x squared plus y squared plus z squared to the negative 3/2. And then I'm going to get plus cy times the derivative of this piece. So That's going to be a minus 3 halves because I know I'm bringing that down. And I've still got that cy, x squared plus y squared plus z squared to the negative 5 halves. Now the chain rule, derivative of the inside part, is going to give me a 2y. So again, that 2 cancels. And if I want, I can combine those two y's. So I've got c times x squared plus y squared plus z squared to the negative 3 halves minus 3cy squared times x squared plus y squared plus z squared to the negative 5 halves. I'm sorry, and I wrote this one wrong. This should have been a 5 halves here, matching the negative 5 halves that I had there. All right, if I take the partial of r with respect to z, it's pretty much the same thing, but with a z instead. So I'm going to get a c times x squared plus y squared plus z squared to the negative 3 halves minus 3c, this time it'll be a z squared times x squared plus y squared plus z squared to the negative 5 halves. So these are the 3 partial derivatives that I get. I need to add them all up in order to get the curl. I'm sorry, not the curl, the divergence. That's what I was trying to calculate. Well, if I add them all up, notice this first term is the same in all of them. So that first term, I'm just getting 3 copies of c, and I'm going to go back to writing this in the denominator. In the denominator, I would have x squared plus y squared plus z squared to the 3 halves. Now, what I'm getting here, these guys aren't all the same, but they're very, very similar. These would be 3 fractions that would have x squared plus y squared plus z squared to the 5 halves in the denominator. And here what I have on top is minus 3cx squared. Here what I have on top is minus 3cy squared. And here what I have on top is minus 3cz squared. So we will have on bottom x squared plus y squared plus z squared to the 5 halves. And on top, minus 3cx squared minus 3cy squared minus 3cz squared. Now, I'm going to just factor out the minus 3c there. So I've got 3c over x squared plus y squared plus z squared to the 3 halves. Plus, if I factor out a minus 3c, that's times x squared plus y squared plus z squared all over x squared plus y squared plus z squared to the 5 halves. Well, I can cancel one factor of x squared plus y squared plus z squared. If I cancel that, then instead of having it to the 5 halves, I'm going to have it to the 3 halves. But now this denominator is the same as this one. I've got 3c on top here, minus 3c on top here, and that's going to be 0. So the divergence of an inverse square field is 0. So divergence of c over r cubed times r is 0. That would be 0 the number, not 0 the vector. Okay. All right, I'm going to keep this component description up here on the board because we're going to need it when we do the curl. So in the next video, we'll come back and we'll calculate the curl of an inverse square field as well.